So we've looked at decay curves for the discharge of a capacitor. So in other words, when a capacitor is charged up, and we've looked how the charge decays, how the potential difference decays, and how the current decays. But what about when it's being charged up? So it's a little bit different. So let's have a look, and let's start with the charge. And so I'm going to draw here a graph of charge against time for the charging of a capacitor. Well, what we've got here is we've got a neat circuit where I've got a little switch, so we can actually move the switch to position A, and that will cause a charging up of the capacitor because current will flow around onto the plate and onto one plate and off the other plate. Electrons, of course, are going the other way, don't forget. Well, what's that going to look like? Well, initially there's no charge on the plate, so this is Q, how much charge is on the capacitor. Well, initially there's no charge, so as soon as if A is the moment, or if T is 0 is the moment that I toggle switch A to position A, then the charge is going to start to build up. And it's a bit like the discharge in the sense that at first it's going to flow on quite quickly because you've got a lot of potential difference pushing it on. But of course, as charge builds up here, it's going to be more difficult to push more charge on. And so the rate is going to slow down until it just kind of reaches the maximum amount, which is when the potential difference across the capacitor is actually equal and opposite to the potential difference across the power supply. So, well, you might want to have a guess. If you want to, pause and have a guess, but it's going to look like something like this. And it'll tend towards a maximum value. We can imagine now, of course, that at that moment we decide, okay, well, I'm now going to toggle the switch and I'm going to move the switch to position B. So let's imagine we do that. So there we go, toggle the switch, oh dear, not take the switch away, toggle the switch to position B. And it's going to discharge, it's just going to discharge just in the same way it did before. Very fast at first, because now all this charge is desperate to disappear off one plate and onto the other to rebalance. So that'll now do something very similar, but as we've already looked at. Bang. And there it goes. And that's going to take the same time interval because they're both charging and discharging through the same resistor there. So that's worth being aware of, that those two time intervals there are going to be the same. Let's just label those there. So the same time. Okay, so that's the charge. That's what the charge is going to do. Let's have a look at the potential difference and see what that's going to do. And well, I'll get rid of those two arrows. Well, we're going to do exactly the same thing. We're going to look at what the potential difference across the capacitor is going to do over time. So let's put a little voltmeter there that measures VC, measuring the potential difference across the capacitor. And let's see what the graph's going to look like. So this is a graph of potential difference against time. And we'll first of all, we're going to assume it's uncharged. And so we're going to toggle it to switch A and start the charging process. So let's suppose, like before, at time equals 0, then we're putting the switch at position A. Well, of course, the potential difference across the capacitor is proportional to the charge. So just like in the decay, it's going to do exactly the same type of thing that the charge is doing. So it's going to look very similar. It's going to do something like that. And then if we discharge later on, then it's going to do something like that. So exactly the same, basic. Good, okay, and then the same time intervals again. Good, okay, so that's fairly straightforward. Well, one thing that sometimes crops up in questions is rather intriguing and worth pausing to look at. And one thing that is sometimes discussed is, well, what would be the potential difference? You know, if we put a voltmeter across the resistor, what would happen that time? And it's an interesting question because if we think, okay, well, let's imagine we just switch it to position A and start the charging process. Well, initially, there's no potential difference across the capacitor and current is flowing pretty fast around the circuit. So at that very first instant, we've got quite a big current passing through R, which means that there must be a large potential difference across R. And that's in fact true. And so the graph for the potential difference across the resistor is going to be a little bit different. Let's draw it here. So this is, remember this is VC. Let's draw this one as VR. This is the potential difference across the resistor. Well, it's going to start off big and kind of drop down. So it's going to start off, now it's actually going to start off at the maximum value, at the value of the potential difference. Another way to think about this is that, remember, in the golden rules of circuits, the EMF is shared, isn't it, amongst components in a series circuit, and these two things are in series here. So when the potential difference across the capacitor is 0, the potential difference across the resistor must be the EMF, must be the potential difference of the power supply. And so it actually starts off high, and that's going to drop down as the capacitor charges. So at the end, when the capacitor has full potential difference across it, then the potential difference across the resistor will be 0. And of course the current has stopped, so we know that kind of makes sense. So it's actually going to do something very similar, like a sort of discharge type curve. In fact, I'll just put that on here, because it's actually like a mirror image curve there. And I haven't done that very well, but so that these two are always going to add up to the total value, to the supply. Hope that makes sense. Good. And then we can say, well, what would happen when we switch the switch back to B? Well, let's switch the switch back to B. Well, now, remember we're looking at the potential difference across the resistor. Well, there's going to be a big initial current again. So now, at that moment that I switch the switch back, well, of course, there's a massive potential difference across the capacitor. That's effectively now acting like a battery and like a cell, and the current is going to whiz around the other way and through the resistor. So at that initial moment, we're going to have a big potential difference across the resistor, and that's going to reduce as the charge flows away and the current goes down. So that's interesting, and it means that we're going to have the following happen. If we flick the switch, we're going to get, it's going to jump to a very big negative value in the opposite direction, and then sort of decay in the opposite direction like that. And then if we went on, it would sort of, if we switched again, we'd do something like that. So let's put those positions. That's position A at time 0, and we're flicking the switch at time B, at position B. So let's have a look at the current finally. Well, the current is going to do something a bit like the potential difference, because we've got the current here, or the potential difference across the resistor, because of course the current is flowing through the resistor. So if we draw our graph, and let's start off with the charging up. Let's go to the charging up. Well, the current is going to start big and gradually slow down. Remember, the current kind of gushes onto the capacitor at first, so it's going to do something a bit like we're getting a bit used to now. And so that's if I put the switch to A. But then when I discharge it, well, we already know that it's an exponential, and so I'm going to get a rapid current at first, but in the opposite direction to during the charging process. Okay, so I could have flipped those two over and had the initial charging negative and the second one positive, but they're opposites to each other. So hopefully that all those graphs make sense. The last thing just to bear in mind is what would happen if we had a smaller resistor in the circuit. Well, let's imagine the charge. Let's think about the charge. Well, a smaller resistor means that the charge can basically move around pretty much quicker, and so you would just get a much more rapid effect, much more rapid charge and discharge. And sometimes we have to think about what happens if there's no resistance. Well, if there's no resistance in the circuit, it would be virtually instantaneous, but I mean it would take a tiny amount of time, which you may or may not be able to appreciate on the graph, because depending on the scale, because there's resistance in the wires. But when capacitors charge up really fast like that, then you tend to get a bit of a spark. And so this is low R, and this is lower resistance. So that's just worth bearing in mind.